All right, this is AB Calc, section 5.60, number 1. If you haven't yet, go see the video, which will be posted right above this, called the Y of U sub. Okay, that'll teach you a little bit about the introduction to the substitution rule for evaluating indefinite as well as definite integrals. Okay, got a little class opener here. I'm going to go ahead and pause the video, write out some derivatives, and you can check your work on that. Okay, as you can see here, I've got each of my antiderivatives for a, x to the n plus 1 over n plus 1 plus c. For b, ln of the absolute value of x plus c. For c, tan x plus c, and so on. You can kind of check your work along the way. I did have one mistake in notation here. It should be g of t dt in example L. So check your work there. If you got any questions, see your teacher. Okay, so let's look at and use what we built in that the y of u sub to work through a couple of integration by substitution questions. So this is kind of leading us right into some more complex methods of integration. We'll see a couple other methods as well along the way. Okay, so example 1. The example I talked about in the video, du ended up matching perfectly with like items that we had for what we called g of x. So recall this, right? If I have the integral of f of g of x times g prime of x dx, I like to try to write that as the integral of f of u du. Now, sometimes g of x and g prime of x are perfectly matched, right? Sometimes they are. Other times they may not be. There might just be a difference in a constant, but it's okay. It's going to be all right. Right? So what we do is we set u equal to g of x, and then we roll. Right? We go du dx equals g prime of x, and then we find du, and hopefully du matches up well with g prime of x times dx. In this case, in example 1, it's not going to match perfectly, but that's going to be okay. All right, so in this case, right, I want to think of the integral of e to the 3x as 1 times e to the 3x dx. Okay, and I'm going to think of g prime of x. I'm going to think of g prime of x as 1, and I'm going to think of g of x as 3x. Now, those are closely related, right? The derivative of g of x is actually 3. It's not 1. But you'll see how this kind of aligns in a moment here. So I'm going to set u equal to 3x. Therefore, du dx is going to equal 3. So I can write that du is equal to 3 dx. Now, in this case, I can't do a substitution directly yet because I have a 1 dx. I don't have a 3 dx. So I want to turn this expression right here into just 1 dx. So I'm going to divide by 3 on both sides. And so I can substitute in 1/3 du for dx. Okay, so I'm going to take this, and I'm actually going to rid myself of the 1. And I'm going to rewrite this integral as e to the power of u, right, because u will substitute in for 3x, times dx. dx is now 1/3 du. So I'm going to bring the 1/3 out in front and leave the du on the inside. So the substitution piece is really interesting, right? Now I've got this in a form where I can use basic techniques of integration in order to solve for the antiderivative. So I'm going to leave the 1/3 on the outside. I'm going to integrate e to the u with respect to u, which is e to the u plus c. Now, again, the last step in the substitution method is to sub back in for u, putting our antiderivative in terms of x. So this would be 1/3 e to the 3x plus c. Okay, now checking that, just to confirm, right? Let's take the derivative with respect to x of 1/3 e to the 3x plus c. Well, the derivative of c is going to be 0. It's just a constant. The derivative of 1/3 e to the 3x will be 3 times 1/3 e to the 3x. 3 and the 1/3 reduce, and I get e to the 3x, which is equivalent to our integrand, so we can check that off our list. There is our antiderivative. Okay, let's look at example 2. Now I'm going to start to move a little quicker. I'm not going to look at all of this notation over here necessarily. I'm just going to start to kind of take this concept and run with it. Okay, so again, my g of x, or my u, is typically nested inside a function. Typically, okay. It could also be, for example, in the denominator. We'll see that coming up soon as well. But I'm going to set u equal to negative 2x. Therefore, du dx is equal to negative 2. Okay, thus, du is equal to negative 2 dx. Now, I don't see, a negative 2 tagging along anywhere as a constant out here. So I'm going to get just dx alone. So I'm going to solve for dx. That means I'm going to have negative 1/2 du is equal to dx. There's a portion of my substitution. Right, I'm going to plug that in for dx. And of course, I'm going to plug in for negative 2x. I'm going to plug in a u. So transferring this into a form in terms of u instead of in terms of x, I'm going to bring my negative 1/2 out in front. I'm going to have my du hanging out on the back end of things. And I'm going to rewrite this as the cosine of u. Okay, now let's integrate. We've got this in a nice form. Okay, the antiderivative of cosine of u is sine of u. So this would be negative 1/2 sine of u plus c. All right, the constant affects nothing. Just keep it on the outside and then bring it back once I find the antiderivative. All right, one more step. So the antiderivative of cosine negative 2x is going to be negative 1/2 sine of negative 2x plus c. You can confirm that by using your abilities in differentiation, but I'm fairly certain that we're good to go on that one. Let's continue to the next slide. All right. Let's take a look here at example number 3. Okay. Now, our g of x and our g prime of x, right, are going to be related. The derivative of one will be related to the other. Okay, so I'm going to, and I typically do this, I look for a nested function. So this is going to be my u. Okay, u is equal to 5 plus 2x cubed. The reason I picked that is because when I differentiate, g prime of x, or the derivative of that, should end up outside along with dx. Okay, or some relationship to that function g prime of x times dx. So let's find du dx. Du dx is equal to what would be 3 times 2 times x squared. Now, the reason I didn't write that as 6x squared is because I can see that I have a 2x squared dx here. 2x squared, and then I'm going to bring that dx on over. So I'm going to write this as 1/3, getting the 3 out of there. I don't want to move that over. Du is equal to 2x squared dx. So you can see I can do a substitution, replacing 2x squared dx with 1/3 du. So I'm going to bring that in. I'm going to go like this, 1/3 du, antiderivative, and I'm going to take the square root of what was 5 plus 2x squared, but will now be u. Okay, let me clean this up just a little bit. Oh, it's not allowing me to do that. Okay, well, we just got some aggressive spacing here, but that's okay. I'm going to hang this and kind of clean it up along the way here. All right, so I'm going to take the integral, or 1/3 the integral, of u to the 1/2 du. All right, taking the integral of the square root. I mean, you can, if you memorize it, that's great. If you don't, use the power rule of integration in the process. So that'll be 1/3 times 2, oops, never mind, times, that'll be 2/3 u to the 3/2 plus c. The derivative of 2/3 u to the 3/2 will be u to the 1/2. Okay, let's confirm it on the side. I'm kind of questioning myself, but I think I'm good. d du of 2/3 u to the 3/2. You should be doing things like this just to confirm. So that'll be 3/2 times 2/3 u to the 3/2 minus 1, which is 1/2. Yeah, we're good. So that would come out to be the square root of u, which is exactly what I want it to be. All right, so I'm going to just simplify this. This will be 2/9 u. Now I'm going to do my my substitution right now, actually. And I'm going to write this as 2/9 5 plus 2x cubed to the 3/2 plus c. There's my antiderivative. I could confirm that by differentiating, but I don't really want to right now. Let's look at another. All right, example 4. This is interesting. This is our first definite integral. So you can see I got a definite integral from pi over 6 to pi over 4. So now there's a few little items of notation that you have to be aware of along the way here. The first thing that I would do is, this is actually complex if you keep it in this form. What I'm going to do is I'm going to rewrite this as the integral from pi over 6. And this is just from experience, and you'll get better at this along the way. But I'm going to write this as secant squared 5x. And the reason why I did that is because I don't know what the integral of 1 over cosine squared is, but I do know what the integral of secant squared is. Okay, so technically they're the same thing, but the format of this is just kind of disguised as something more complex than it needs to be. Okay, so I'm going to think of this as 1 times secant squared 5x. So like when I think of f of g of x, I'm thinking of secant squared of 5x. So I think of, f as secant squared and g as 5x. So is the derivative of 5x related to 1? Yeah, it is. They're both constants, so we can manipulate and work with that in just a moment here. Okay, so I'm going to set u equal to 5x, and I'm going to then differentiate du dx is equal to 5. Therefore, du is equal to 5 dx. Well, I don't have the ability to just kind of take things and work with them in that format because I have a 1 dx, not a 5 dx. So I want to replace 1 dx, and therefore what I'll do is I will divide by 5. That gives me 1/5 du equals 1 dx. And I'm going to sub 1/5 du in for 1 dx. All right, now, before we go too far, of course, this would be the integral, and I'm intentionally not putting limits on this yet. This would be 1/5 the integral of secant squared u du. Right, here's my substitution. 1/5 du is equal to dx, and u is equal to 5x, so I plug that right in there. Now, if you were to tag pi over 6 and pi over 4 right now, you'd be incorrect, because these are the limits on x, not on u. All right, so don't be doing that. That's bad form. Okay, so what we want to do is this. We know that if x equals pi over 6 and u equals 5x, then u equals 5 pi over 6. So what I'm doing is I'm really building my limits for u. So this would be from 5 pi over 6. And if x equals pi over 4 and u equals 5x, then u equals 5 pi over 4. So now I've got my limits for my new integral in terms of u. Okay, so I can integrate, and then I can use FTC part 1 in the process. Okay, so I'm going to integrate. That's going to be 1/5. Integral of secant squared is tangent of u, evaluated from 5 pi over 6 to 5 pi over 4. Okay, so we got to remember some trig here. I'm going to pull 1/5 out. And I'm going to take tangent of 5 pi over 4 minus tangent of 5 pi over 6. So let's sketch some stuff out using the unit circle. Alright, so here is 5 pi over 6. Right, there's our angle, 5 pi over 6. That, in the unit circle, that's a 1, that's a half, that's a negative root 3 over 2. Okay, so the tangent of this angle, right, would be a half over negative root 3 over 2. I'm not exactly happy with my notation right now. This is, I'll call this theta. This is equivalent to the tangent of theta. Okay, so if I reduce that, what do I get? I get, that's equal to negative 1 over root 3. Okay, so 5 pi over 6. I'll fill in this here in a moment. This is negative 1 over root 3. Okay, and then 5 pi over 4, we'll do that in a separate image. 5 pi over 4 is right about here. And I'd have a 1, negative 1 over root 2, and a negative 1 over root 2. Right, so this angle right here would be 5 pi over 4. So this reference angle would have a tangent. We'll call that not theta. Let's call it phi. The tangent of phi will equal a positive 1. Okay, so this would be 1 minus a negative 1 over root 3. All right, so I could actually leave it like that. I'm going to clean this up just slightly. And I'm going to call this root 3 over root 3. And that'll be plus 1 over root 3. Which would come out to be, what would that be? Root 3 plus 1 over 5 root 3. I think that would be acceptable. So that would be the area under the curve secant squared 5x from pi over 6 to pi over 4. Interesting problem, interesting use of, again, just a hint. Anytime something looks real complex like this, especially in a trig format, see if you can put it in terms of a single trig function that's not reciprocal in nature. Okay, let's continue on to the next slide. All right, example 5, we've got another definite integral. And again, like what you want to do when you have a product of two functions, you're hoping they're related, and in this course they will be. In BC, you might have two unrelated functions, and then you have to use a different technique of integration. But in this case, you're going to be able to find the antiderivative of this expression. So notice that the derivative of tangent is secant squared, right? So I would call, you could think of, f of x, and this is not necessary, but I'm just laying it out. You think of g of x, so f of x is x, g of x is tangent x. So f of g of x is still just tangent of x. Okay, and think of g prime of x as secant squared x. Okay, so I want to set u equal to tan x. Thus, du dx, this lines up perfectly, is secant squared x. So du is equal to secant squared x dx. Look at that perfect substitution. Secant squared dx lines up perfectly. Okay, so I'm going to do my substitution. I'm going to set u equal to tan. Du is equal to secant squared dx. Okay, so this allows me, of course, I'm going to use a different method here. What I could do is if x equals 0, right, then tan x equals 0, right? So if x equals 0, hold on, I don't like the way I wrote that. and u equals tan x, then u equals tan of 0, right? So when x equals 0, u also equals 0. Okay, when x equals pi over 3, and if u equals tan x, then u at pi over 3 is whatever tangent of pi over 3 is. So I sketch it, and here we go. This angle here is pi over 3, we'll call it theta. This would be a half, this would be a root 3 over 2, this would be a 1. So the tangent of theta, which is pi over 3, would be root 3 over 2 over 1/2, which is actually just root 3. So I could work with this, which would be the integral from 0 to root 3 of course, we would go with u du, right? And here's where I get my substitution from. The u comes directly from here, and du is a direct substitution and a perfect match for secant squared x dx. Okay, so now I could run with this, and in terms of u and the limits of u, that's fine. Another alternative, okay, actually I'll just complete this as is. This would be u squared over 2 evaluated from 0 to root 3. Okay, so we would simply plug in root 3. Take root 3 squared over 2, that's a 2, minus 0 squared over 2, and we get 3/2. Now watch this. If you decided, let's say right here, you said, hey, I'm going to drop my limits for a moment. All right, this is going to be the integral of u du. Well, the integral of u du, like we know, is u squared over 2. Now, what I'm going to do is I'm going to rewrite this as then, since u is tangent, I'm going to rewrite it as tangent squared x over 2. Okay, now I bring my limits back. So I'm not putting the limits of x here and here because that would be incorrect. So I drop the limits momentarily. This is kind of like option 2. I prefer option 1, where I utilize the limits on u. It just keeps things simple. Okay, I don't have to do quite as much trig like I will in this case. Or I can use option number 2 and just go with the original limits from 0 to pi over 3. What you end up doing is, the trig that you did over here to find the limits of u, you just end up working with at this point. So this would be tangent of pi over 3 quantity squared over 2 plus tangent squared of 0 over 2. Well, the tangent of pi over 3 we know is root 3, so you can see how you end up in the same place anyways. Plus, of course, the tangent of 0 is 0. And what we end up getting is, of course, root 3 squared, which is 3 over 2 minus 0. So you get the same place, right? It's whether you want to do your trig to find the limits on u, or whether you want to do your trig during the integration process. Okay, one more example here, folks. All right, real interesting example finishing up here. This is an example where it's really interesting, but f of x is actually equal to 1 over x. So I want to think of this integral as x times 1 over x squared minus 4 dx. And I'm going to say f of x is 1 over x. I'm going to say g of x is x squared minus 4. This is going to end up being my u. Okay, and I'm going to say that g prime of x is going to be x. Okay, now if this method just doesn't jive with you, that's fine. You don't have to use like this setup. This is just a way for you to see things, okay? All right, so what I want to do is I'm going to set u equal to x squared minus 4. Therefore, du dx, as we've done in the past, is 2x. Now, this isn't going to be a perfect match to g prime dx. It's not. All right, it's not going to be a perfect match because that's that 2 there. So du is equal to 2x dx. Well, I want just x dx. So like I've done before, I'm going to divide by 2, and I get x dx. Nice. So I can replace x dx with 1/2 du. So the original integral is going to be equivalent to 1/2 the integral of, now check this out, this will be 1 over u. 1 over u du. Okay, so let's see where we came from. Okay, 1/2 du, right, is equivalent to x dx, and 1 over u is equivalent to 1 over x squared minus 4. Okay, so we took a complex integral like this thing, right, and we buried it. We simplified it down to a very simple integral. Right, this is just going to equal 1/2 the natural log of the absolute value of u plus c. And since this is an indefinite integral, I don't have to worry about limits. I'm just going to rewrite in terms of x alone, which would be the natural log of x squared minus 4 plus c. Guys, that is the u substitution technique for integration. We'll do plenty of examples in class. Ask your teacher if you got any questions, and we'll see you in the next video.